Okay, one of the characteristics we're going to look at next is called the coefficient of determination. While it is related and defined by R, which is our correlation coefficient, the coefficient of determination actually tells us something completely different about our data and what type of relationship is currently going on. All right, so the definition of the coefficient of determination, and I think I can go ahead and activate this, is that it gives the proportion of variation on y that can be attributed to an approximate linear relationship between x and y. Okay, that sounds complicated, and we'll go through an example of this, but the coefficient of determination in this particular statement is trying to say that because we did a linear relationship, y is, or x is able to predict y this much better. Okay. And so let's kind of look at our range of motion data and kind of think through an example here of what I mean by we're able to predict it this much better. Okay. So suppose we were asked to predict a future y, but no one bothered to tell us x. That sounds kind of weird. They said, all right, I want you to tell me what's going to happen, but I'm not going to tell you what. I don't know who could show up. I don't know what age they are. I just want you to tell me what do I expect to see for the range of motion. Well, when we don't have an x to predict it off of, you got to think about, well, what other predictors do we have? And about the only best predictor we have is, well, what about the average y value? We could just add up all the y's, divide by the total number, and go, well, I don't know who's going to walk in the door, but I do know that on average I would expect to see this. So if we calculate y hat, we'd get 130.083. Okay. And if I go back in and I calculate the residuals on each of those points, so I look at how far off they are from that y bar, from that just that average, I'll get this like this regression squares line. I'll get the sum of the residuals. So if I add up all those errors, square them, and add that all together, I get this number. Okay, this 1564. Okay, so let's switch then to the regression line, the one that we already figured out. Because if I do know x, it makes sense that I would take the x value and evaluate it into the regression equation, and then predict what it would be, which then changes my equation to this. Now again, we're going to look at the residuals, so we're going to calculate the residuals of all those points, and just like before, we're going to square them and add them up, and I get this number. Okay, now if you remember that sum of the squared residuals, that's the smallest when we're dealing with the least squares regression line. This is the best number that minimizes the error to each of those points. Okay, so the question then is, well, what happened when I take the average y, the y bar, and I compare it to the LSRL y? You know, how much better did I get when I switched from the y bar, the average y, to the predicted y? Okay, so our sum of regression went from 1564 to 1085. So what percent is that? And that would be this little calculation here. Let's take all those numbers. We get 0.3062. Okay. This is what we define as r squared. Okay, so again, r squared is, we're comparing the average y to the predicted y's. How much better is our data when we switch from average y's to predicted y's? How much better can we predict it when we switch to that LSRL model? Okay, so the way we describe this then is, because we're able to predict our r squared was then 0.3, so 30.6% of the variation. in the range of motion after knee surgery can be explained by using an LSRL. Okay, so this brings us to another interpretation. How does one interpret R squared? So just like all the other slope, correlation coefficient, just sound like robots. We're going to input words and numbers where those red symbols are. But other than that, we're going to memorize this, and we're going to use this every time to describe what R squared is. Okay. This is something that does come up occasionally, and you might see this in the textbook, is someone will calculate ahead of time all this raw data, and we'll just get the summary statistics on it. So it's kind of nice to talk about what it is we're looking at. So our LSRL equation, from here, to find our slope, we look at that particular location, looking next to the phrase constant, and then there's some other word that's going to be there, and that word's going to be what x is represented by. And so our LSRL is the constant represents the this y-intercept, and the 0.87 represents the slope of our equation. Okay, correlation coefficient and coefficient of determination. For our class, we're not going to worry about adjusted R squared. That's a more advanced statistic topic. We're going to worry about the 30.6, which is the R squared. And if we know R squared, then we can know R, and that's just by taking the square root. So R in this case would be 0.5. Okay, let me actually pause for just a second, and let me get... Okay, so I just want to take a second and tie in a concept. We talked earlier about a correlation coefficient of 0.5. Anything from 0.5 to 0.8 is what's called moderate, right? Anything below 0.5 we describe as a weak correlation. But the interesting thing is, when we look at the coefficient of determination, if I'm at that border of 0.5, so right where we get to start saying moderate, our coefficient of determination is only 25%. So because we switched to an LSI, because we switched to a linear model, we're only able to accurately justify 25% of the variation in y's by looking at an LSRL. Okay. Interestingly enough, we define 0.8 as strong, a strong R, but the coefficient of determination that goes with that is 0.64, so 64%. So when we're basically when we're determining whether or not the data is a good predictor, we only have to be able to justify 64% of the variation in order to say, well, yeah, we're pretty good at predicting. I can explain 64% of that variation, which is why we call it a strong one. Anyway, just an interesting little side note about R and R squared. Okay, so jumping right back to the notes, let's talk about what an outlier is. Now, normally, in order to use the word outlier, I should have looked at a box plot and calculated IQR, and then I needed to have shown that that particular data value is 1.5 IQR away from Q1 or Q3. In a regression setting, you'll also hear the word outlier. And when we talk about an outlier in this particular setting, we're saying that it's a point that has a large residual, that its predicted value and actual value are very different from one another. Okay. In another sense, just because it's an outlier doesn't always mean it's influential. We have an influential point. This is a new concept for us. An influential point is a point that influences the location of the LSRL, changes the slope from positive to negative, something like that. And the way we identify a point as influential is we remove it and see if it significantly changes anything about our line. Okay, so here's a new set of data, and I'm going to let you kind of take a second and type that in and see if you can get the scatter plot of it, and then get the LSRL and the correlation coefficient. Okay, so at this point you should have the graph, and does it look like there is a point that's influential? Okay, so here is hopefully what you got when you looked at the graph of this, and it looks like there is one point way off the graph, somewhere down at 189,30, that seems to not be with the other points. So if we take it away and we redo the LSRL and it moves it a lot, then we get to describe that one single point as being an influential point. So I'll let you go ahead and do that. Remember to delete the point. And when we recalculate it, we get an entirely new line. And I'd say that that definitely was an influential point. It definitely had an impact on the slope and how steep the line was. Okay, so in just in quick summary, resistant means not influenced by extreme values. So which of the following are not, would extreme values or outliers or influential points not really make a difference? And it turns out none of them. All of those measures can be impacted by extreme data. So it helps to know, as we're looking at data, how do we measure extreme values? How do we know something's an outlier? And then it's a good question of, well, is this outlier valid? Is there a reason why we can ignore it or not? Sometimes the outliers are all the matter in the world, and sometimes they're not. Sometimes it's just, as we've looked at earlier, some biased or bad data collection or